Hi all, welcome to another video. So today we are solving LRU cache. This is not a very core LLD problem because somewhere it is connected to data structures and also maybe concurrency. Okay, so yes, basically if the problem statement would be design cache, then it could be a LLD problem because then we would have multiple different types of eviction algorithms and different writing policies to implement. But here, since it's a simple system design LRU cache, we will not complicate the system and we will take a look at the LRU cache itself. Okay, so let's get started. So before starting with the cache, obviously we need to understand the cache system, right? So in a LRU cache, what happens is basically we have a cache of a limited size, okay? And whenever some data comes in, let's say our cache is of size 5 and a data comes and our cache is already full. So how will we remove or how will we evict any data from our cache? That will be determined by the least recently used algorithm. That is how it is known as LRU cache. Okay, now here what I have written is this is just understanding a cache system. So basically there are different strategies for reading data and for writing data in a cache. So these are like good reads because if in an interview you are asked an LRU cache, interviewer may have follow-ups based on these. Okay, so this you can read about some read policies and write policies. We can go through it one by one. So there are two read policies. One is cache aside strategy, another is read through strategy. So in cache aside strategy, what happens is application, our code application will interact with the cache and the DB independently, which means let's say application needs some data. So first it will check the cache. Okay, if it is a cache hit, the data is available in the cache, so it will get the data from cache and it is done. But if it is a cache miss, the application will retrieve the data from the database. So here application is performing the task. Okay, in read through strategy, what happens is the cache interacts with the DB. Basically if the application or the client requests data and it's a cache hit, the cache will return the data. But if it is a cache miss, the cache will retrieve the data from the database. So only this particular thing changes in these two strategies. Okay, now coming to certain write strategies. So first one is write around strategy. Now in a write around strategy, what happens is, so let's understand this through the diagram. So wherever user gives some data or sends a post request to the application, so that data goes to the DB. Okay, so data is inserted into the DB and that is done. Now if the user requests for the same data during read, okay, if the user will request data conditionally, only then it will be fetched from the DB and put it into the cache. Okay, so this is the scenario. So by default we are not sending the data to the cache. Okay, then we have write back strategy. Now what happens in write back? So in write back strategy, yeah yeah so in write back strategy, new data is inserted by the user. Okay, so it will go to the cache first. So see, write back, so the data is sent to the cache first and from the cache to the database the data is taken asynchronously. Asynchronously means our network call will complete once the data is written to the cache. Okay, from the cache, let's say some event processor might take it up. Maybe we are entering all the data into a queue and the event processor will take it up and update the DB. So this step is asynchronous and here we achieve eventual consistency. Okay, third policy is write through strategy. So here this is the simplest form and it is strongly consistent, where whenever application gets some post request, the data is written to the cache as well as to the database and then only the request is complete. Okay, so this is synchronous, and here everything is done sequentially. Okay, so this was about the cache, or how cache system basically is. So this may be helpful with the follow-ups and stuff. Okay, now let's get started with the LRU cache. So let's talk about the functional requirements. Okay, so as I said, the very first thing I said, cache has a configurable maximum capacity. Oh, obviously there would be a limit, right? So that is a requirement. Okay, this is a function requirement that the cache will have a maximum capacity. Each entry consists of a key value pair, and key is supposed to be unique. So whenever we add some entry to a cache, it is in a key value pair, something like this. Okay, so that we can easily get the data, okay, by the key. Okay, now this is a very important point. The cache should be generic. So when we say we will have a key value pair, what would be the key data type and what would be the value data type? Will it be, let's say we are storing int to int, or we are storing int to integer, or sorry, int to string, or we can have any data type, right? That is why what we are designing is a generic cache. Okay, so our data types will be generic. Okay, but only catches that keys should be hashable. Okay, keys should be hashable. Now cache in general supports different eviction policies, but here we will only focus on LRU. Okay, uh, and what all methods will be support? Put, get, and remove. Okay, so during put, if the key is already present, we will consider that it has been accessed, and during get, if the key is not found, then we can return null. Okay, and yes, both get and put must run in O of one time complexity on an average. This is very important because this time complexity will be the expected time complexity in an interview. Okay, and this is about the thread safety. Okay, we are not going into much details in this video for thread safety. Maybe in another video we will discuss this. Okay, now let's get started with the entities. Now this is a very simple system. Okay, so let's not complicate this. We have defined certain entities, so we are starting from the basic building blocks. Okay, first one is node. What is node? It is an individual cache entry. A node will have a key value pair and some pointer to adjacent nodes. Now this you will understand in the next 2-3 entities. Okay, so okay, I'll give you a basic idea of how we implement an LRU cache. So in an LRU cache we need two things. Okay, for an LRU cache we need two things. One is a hash map and another is a doubly linked list. Now why a doubly linked list? So in a LRU cache, you see we are saying least recently used, right? Which means we need to have an idea about the order in which the items were used. So to get an idea about the order, we are using doubly linked list. Okay, doubly linked list is basically where a node has both breadth and next pointers. Correct? Why are we using a hash map? Because when we will have to, now you see there is a limitation with doubly linked list, that suppose if you want to delete a node, you will have to traverse through the entire doubly list to figure out where the node is present, and then you can delete it, right? So hash map is used to have easier, or let's say to have faster access to a particular node. Okay, so a combination of hash map and doubly linked list will help us in implementing the LRU cache. This is the very basic. Okay, so if you are asked LRU cache in a DSA round, then also this will this will matter. We will have to just use hash map and a doubly linked list. Okay, so yeah, here we are using a node. Okay, let's remove this from here. Yeah, so we have created a node. So a node is an individual cache entry, and that is why we are saying it has pointers to adjacent nodes, because these nodes will be used in doubly linked list. Okay, so each doubly linked list node has a previous and next entry, right? That is why. So yes, we will have node, we will use doubly linked list. So we'll create our own class of doubly linked list and LRU cache. So this is the core class, let's say, where we will have the get, put and remove APIs, and this is the main class which will call this class and get demo our application. So let's take a look at the class diagram. So this is the class diagram. It is a very short and sweet class diagram. Okay, that is, we don't have too much going on here. Okay, so as I already explained, LRU Cache demo, it is the main class. Okay, from where we will run our code. Okay, then we have a LRU Cache. Now here, notice this small kv, right? So this we are using so that our LRU cache is generic. Okay, so our cache has some capacity. It will use a hash map and a doubly linked list. You can memorize these three things because LRU cache is a very important question and it is asked in Goldman Sachs. It was asked to me in Goldman Sachs. Okay, and a slight variation was also asked. Okay, so yeah, we are having capacity here. We have map. So map, and what are we storing inside map? As I said, key so that we can access the node. And what are we trying to access? The node, right? So node. So this is a map and a doubly linked list. Okay, now here is the implementation of a doubly linked list. So in LRU Dash we are giving these methods: get, put and remove. Now a doubly linked list. So a doubly linked list has a head and a tail, obviously, so that we know, basically we will start with a head and tail so that we can perform the other actions easily. We will not have to worry about creating a head, creating a tail, if it is the first node and all that. Okay, and in doubly linked list we have implemented certain methods. Now these methods will be beneficial to us when we are working on the get, put and remove operations. So let me give you a small idea. When we will do get on any particular node, so that means that we have accessed the node, correct? Which means it has now become the most recently used node. Now as I mentioned that we will use a doubly linked list to maintain the order of access, right? So wherever the node was originally in the doubly linked list, we will pick it up from its position and place it in the front. So what we are essentially saying is that in our doubly linked list, the node at the head, this will be most recently used, and in sequential order, the last node before the tail will be the least recently used. So this is what we are following. That is why we need certain methods like move to front, remove last node, remove node for our convenience. So whenever we are trying get, right, wherever the node was, we will remove it, we will remove that node and move it to the front. We will remove the node and move it to the front. Okay. Similarly, when we are running put, if the key is already present, it has been accessed. So remove the node and add it to the front. Okay. Other than that, yeah, so we have remove as well, and in doubly linked list we have implemented certain methods for our help, and this is the smallest unit in our code, which is a node. So a node has a key, it has a value, it has a previous pointer and it has a next pointer. Okay, so you can take a look at the class diagram. It's a very simple, very easy class diagram. Okay, now let's move ahead to the code. Okay, so as I said, we only have 4 files over here, 4 classes and 4 files. So let's start with the smallest one, which is the node.java. So in node.java we have k key. Now here notice, please read about generics if you haven't. So here we are using generics. So since key and value can have any data type, that is why we are using a generic over here. So we are saying k for key and v for value. Okay, so a node will have a key, a value, it will have a previous node and it will have a next node. Also we have given a constructor. Okay, now let's see the doubly linked list class. So in doubly linked list we have mentioned, we have created 2 nodes, the head and the tail node. Okay, and in the constructor we are constructing or basically instantiating the head and the tail nodes. Also this is a very important point, and this I often tend to forget, that we have to link our head to tail and our tail to tail to head, yeah, like this. So we have to do this. I often forget this, and it's not good if in an interview you forget this and come back to update it. So just remember this thoroughly, that we have to form these links earlier, here itself, in the constructor itself. Okay. Now then we have this code add to front. So whenever a node, if we are trying, so let's say whenever a node is most recently used, okay, then we will try to add it to the front, correct? So how am I adding it to the front? This is very easy. We are simply taking the current front node. Okay, so let's say we have a head and a current front node, and I have a node trying to come here. Okay, so what we will do, we will add head to node, right? So there are two links. If you have a link from head to current front node, we also have a link from current front node to head, right? So we don't have to do anything. Let me just zoom in a bit. Yeah, so here what we have to do is we have to break this link head dot next, and we put it to node dot next, we put it to current front node. Okay, current node previous. So here we add up this link is now broken. These two links are now broken. This previous node, this previous points to the node. Okay, and then node previous points to head. So something like this we try to formulate. So this will be very easy. If you use a copy pen, it will be very easy. It will be very easy for you to come up with this. Okay, now we have remove node functionality, where whenever we pass a node we can remove it. So how do we remove a node? So let's say whatever node we have, we will have some node 1, the node which we want to delete, and a node 2, which is the next node. So how to delete? We have 4 links, right? We have 4 links. So we will have to remove 2 of these links, correct? 2 of these links we have to remove. Which links? So we make node 1 next point to node 2. So prem node next points to next node, and node 2's previous points to node 1. So next node previous points to previous node, and these 2 links, the links attached with node, I am just marking them as null. Okay, this you can avoid or write, it's as per your convenience. Now I've given a small functionality for remove last node, because last node is our LRU node. Okay, so whenever our cache size is full, we will have to perform this. That is why I've just given a separate implementation for removing the last node. Okay, now this is just a helper function which I have implemented, so that when I give demo, you should be able to take a look at understand what the entries are in our cache as of now. Okay, now let's take a look at the core LRU cache. So here here I have marked the capacity as 3. Okay, so this you can either take input from the user, or you can just have a final variable defined for it. So I have taken it as 3, and as I said, we need 2 things. We need a hash map and we need a doubly linked list. So here we have a map and we have a doubly linked list, both of which we are instantiating inside the constructor. Now this is the get operation. So whenever we run a get operation, we will get the key. So if it is not present, if the value is not present in hash map, it means we have to return none. But if it is present, we will find out the node from the map. Okay, now see here you will understand why we need a doubly linked list and why we need a map. From the map, it is easy to get the node's reference, right? Now as I have the node's reference at my hand easily, I can just remove the node and I can add it to the front. See, now it has become the most recently used node. How simple it was, right? We have removed it and we have added it to the front, and yeah, this is done, and we can return the value. Similarly, let's see the implementation for put. So here what we are doing is again we are trying to check is the key already present in our hash map. If the key is already present, which it means we have to update the value. So get the node for which we have to update the value and update the value. That's it. Now you could have set of functions and stuff for this. Implementation is up to you. Okay, now this is the most recently used, so remove the node and add it to the front. That's it. But If the node was not already there, sorry, if the key was not already there, now we have to add the key. But before adding the key, check, is our hash map complete? Hash map size is full, basically means LRU size is full. If it is equal to the capacity, we have reached the cache capacity. Okay, so figure out the last node. So you can also get this from the, so basically what you can do is, when you are removing the last node, at the end you can return the last node. So here, from here you can get the last node. Okay, here I implemented a different way to get it. It is not a very appreciated method. Okay, so you can return the last node from here. Okay, so that way it will be easier for us to fetch the last node. Okay, and once I fetched the last node, I have to remove it from the hash map and I have to remove it from the doubly linked list. This is a very important point. I often forget this, and that is why I am highlighting this. Okay, this question is a very important question. I'm again saying it because this was asked to me, and this is asked to a lot of people in a lot of different companies. Okay, and after all of that, what we are doing is, we are creating the node, we are adding it to the hash map, and we are adding it to the doubly linked list. Okay, now let's take a look at the remove operation. There's nothing different we have done here. We are simply checking. If it is not present, we just return. If it is present, we get and we remove it from the hash map and from the node. That is it. Okay, now let's go to our main class. So here I have given certain dummy commands and stuff to simulate a cache. So basically I'm creating a LRU cache, putting some key, printing the cache, putting key 2, key 3. So whenever we put, these items become most recently used, so they will come at the head side of the doubly linked list. And when we get, again this becomes most recently used. Okay, so let me run this. Let me run this. So here are the execution results. Now see, when I inserted apples, this is our cache. This is how our cache looks. 1 apples. Okay, then we inserted bananas and then we inserted cherries. So this is how it looks, because cherries has been inserted last, which means it has been accessed most recently. Okay, this is most recently used and this is least recently used. Okay, and then we run get for key 2, so we get bananas. Let's just check. Yeah, so we run get for key 2. Okay, after that yeah, so see, we ran get. Okay, so now this has become most recently used, so bananas has come at the most recently used. And now we are trying to add something, but cache capacity has reached, so it will evict a node. Okay, so look here, it has evicted apples. Bananas has shifted its position, cherries has shifted its position, and dragon fruits have entered the cache. Okay, again we try to insert apples at key 1. So this is how it is inserting. Okay, so yeah, this is it. This is a functional LRU cache to handle concurrent access and thread safety. Here I have simply made my get, put and remove functions synchronized, so at a time any one thread can access these methods. But we can have another separate video entirely for the concurrency discussions, because it can be a very long discussion in an interview. So from an interview perspective, we can do that in the next video. Let's see. Okay, so for now, this is good, this is done. Please expect this question whenever, or please prepare this question. At least if you are preparing for SDE-2 interviews, please prepare this question. Okay, yeah, that will be it. Thank you everyone.